Thank you, Mary. So I'm going to just say a few things about Akira Okubo here. And this is Akira on the cover of Oceanography magazine or journal. This was this whole issue of the journal was dedicated to him in 1999 as a tribute to him. And there is his lifespan there on the front page of the journal. And this documents some major times in his life, obviously. He was born in Japan and he immigrated to the US in 1959. And he got his PhD from Johns Hopkins under Don Pritchard, who was also a professor here eventually, as well as the dean here eventually. And he was appointed by Jerry Schubel, who was dean here as well in the early formation of the Marine Sciences Research Center. And he was appointed in 1975. And he was very well known for his studies in physical oceanography, in particular, and looking at turbulence, oceanic turbulence and diffusion. But he also was extremely interested in biological processes, particularly dispersion of animals, insects, and so forth. And he was an incredibly loved professor here and had a major impact, intellectual impact on marine sciences here. And he did it in a way that was quiet and unassuming, which made him even more powerful in his impacts on people. And now my familiarity with him actually was as an undergraduate looking at turbulence theory, and he had a really great article on oceanic diffusion in deep sea research in 1971. And many of you may be familiar with this plot, which looked at the functional relationship between horizontal diffusion rates here, eddy diffusion rates, and length scale of your observations and in the ocean. And this really bore directly on the fundamental theory of turbulence, which you can read the paper to learn more about this. And here, there was a symposium here in 1995 to celebrate Akira, and there's a young or younger Malcolm Bowman presenting Akira with. It was a tradition with Jerry Schubel that everybody got a plaque or something like that on whatever occasion, and so here was Akira's plaque. And so you may know if you're familiar with some of his contributions, these texts, for example, diffusion, ecological problems, mathematical models, and he, I really enjoyed Akira because he embraced analytical mathematics and had some beautiful solutions to mathematical problems that weren't necessarily numerical. And at the time, if you appreciate pure mathematics, you'll appreciate his approaches to problems. And this was a solution that he wrote out in response to something that Wilson, who was a physical oceanography faculty here, posed regarding transport in Long Island Sound. And so this is the second edition of his famous book. So there was a lot of impact and call for a new edition of that in response to the people who wanted to see an update. And so he wrote that with Simon Levine, who was a famous mathematical ecologist from Princeton. And so this is another example of the scales of, in this case, the Reynolds number of the system relative to the size scale and different kinds of objects moving through water. And I remember we had a talk here by the father of one of my graduate students who was a captain and head of one of our nuclear submarines that carried weapons in the ocean. And Akira got up and said, "Oh, well, I can tell what the effect of this submarine is on turbulence in the ocean, and therefore track it and know how fast it can go and so forth." And he was shocked. The captain was just shocked to hear this because it was classified information, and Akira he was able to surmise the performance of the submarines. And so here we are. Here's Akira with Don Pritchard, his advisor, and one of our early physical oceanographers here, Harry Carter, and Bob Wilson, who I mentioned earlier. And you have to understand Akira's impact on the community because it's reflected in the people that came here to celebrate in this symposium. These names here, like Simon Levine, Thomas Powell, John Steele, Mimi Cole, and Trevor Platt, and Curtis Ebsmeyer. These are like, at the time, these are the top people in the fields. And so they came to honor him. And he also had quite a sense of humor as a person, and he loved Hana, Japanese restaurant in Port Jefferson, and he gave directions to how to get to Hana restaurant to people. And this is one of his sketches of directions to Hana. And there he is in his office, which is the Okubo room down the hall here. So I hope that gives you some sense of Akira's impact and the fact that everybody basically loved it's incredible. So this is what we're having honor for. Welcome. Thank you for
Thank you, Bob. So I'm gonna pass it over to Jackson, and maybe you can introduce Jim and also just say a little bit about how Jim got here today.
So I have the honor and the privilege to introduce our speaker today, who is Dr. Jim Hurrell from Colorado State University. He serves as the Scott Presidential Chair of Environmental Science and Engineering at CSU. And prior to CSU, he had a very long and decorated career at the National Center for Atmospheric Research, where he served as the director of the Climate and Global Dynamics Lab. He was the chief scientist of the Community Earth System Model team, and most recently served as the director of NCAR between 2013 and 2018. So, of course, a very decorated atmospheric scientist. He also truly does embody the characteristics of the Okubo scholar, who is chosen by the students as not just a decorated scientist, but also one who demonstrates the great characteristics of being a mentor. And he's proved that during his short but a very impactful visit here with his career seminar yesterday, which he gave to a bunch of graduate students, where he kind of showed his transition from a postdoc at NCAR all the way up to the director. And I think the other students would agree that he's been impactful here. He even came to the open mic night last night, so that's all right. With that, I think I'll hand it over to him to give a talk about solar climate impact. Great, thanks for coming.
I have it on. Yeah. So does the sound good? Okay. So thank you all so much for coming. I want to start with just truly saying what a tremendous honor it is for me to have been invited to give this Okubo seminar. It means the world to me, especially coming from the student body. No offense to my professor colleagues, but it's wonderful to be invited by the students. And I'm sorry the trip is just a couple of days long. I'm going to have to come back and spend more time because it's been a really great visit. I do think it's a bit unfair to expect me to entertain you through a seminar after the open mic night. That was really fantastic, and I enjoyed it so much that I went back to my hotel room last night and pulled up Spotify, but I couldn't find Planktones or anything like that on Spotify. So I'm looking forward to those album releases sometime soon. So I want to talk to you. So I'm a climate dynamicist, and much of my research is, traditional climate dynamics, trying to understand the role of the ocean in producing climate variability, decadal climate variability, the predictability of climate, the impacts of climate change, and things along those lines. But I wanted to share with you today some work that I've become more recently interested in, and hopefully convey why it's an emergent topic in our field and why I think it is important to research it. And that is solar climate intervention, or solar geoengineering. And it's a topic that some people have very strong feelings about, all the way from saying we shouldn't be researching this topic, while another part of the community is recognizing that it's here, people are asking questions about it. So I want to take you through some of the sort of the foundational thoughts around this topic. And then at the end of the talk today, share with you some of the work that my research group at CSU is doing on it. And I know in this audience, everyone is very much aware that we are living through a period of tremendous transition in terms of the chemical composition of the atmosphere, in particular the buildup of greenhouse gases, carbon dioxide, and other gases. And as the impacts of climate change are becoming more and more pronounced, more and more severe with every 10th of a degree of global warming, it's really causing the scientific community to ask this question, and perhaps an uncomfortable question. And that is, should we intentionally intervene into the climate system to potentially minimize some of the worst impacts of climate change? So I want to take you through that story a little bit today. I don't do hardly any of the research myself. I can thank a wonderful group of students and postdocs that I have. I'm not going to go through all the names here, but my birthday is in March. So every year I'm so absent-minded. I show up on my birthday and they're like, surprise. I'm like, I'm truly surprised. I should have this. But this was a party showing my current group. I think everyone is there, maybe one or two are missing. But these are some individuals that I'll mention as I go through the talk that have graduated in the last year successfully with their degrees. And I'm going to feature some of their work as well. So credit really to my students and postdocs for the great work they're doing. So I want to start off in a bit of an interactive way. So if you're connected to the internet, I'd like you to get your phone set up. I'm going to ask you some questions to begin with. So give you a second to join Slido here. Hopefully this works. If you're too far in the back to get this, feel free to walk up. See people still trying to scan this. Is it working?
Yeah.
Are people on Slido? Okay. And if you're not there yet, don't panic, because this code comes up on the subsequent slides. So the first thing that I want to ask today, and this should be a live poll, is how familiar are you with this concept about solar climate intervention, solar geoengineering, proposed ideas of reflecting sunlight in order to cool the planet? Understanding.
We're supposed to hit the button on
You're supposed to, yeah, so the phone should have a poll. People are filling in that poll. And it looks like the leading answer is going to be about 50% of the people that have contributed to the poll say you have a basic understanding of it. A significant amount maybe have heard the idea, but don't really know much about it. And so 2%, who actively works on this topic? Curious. Yes. Yeah, Ruben. Ruben and I had a great talk about it this morning. Okay. So this is good. This is kind of what I wanted to achieve. It's a topic that is really growing in terms of conversation. More and more scientists are getting involved with it. IPCC is going to have a chapter in the next assessment report featuring this topic. So I thought it would be good to share a little bit about it today. I want to ask one more question before I get into the talk. When you hear the term geoengineering or climate intervention, what's the first word that comes to mind? Is it crazy, scary, promising? That should be a word about risky, yikes, complicated, expensive volcanoes, controversial. Looks like risky is winning so far. Expensive, unrealistic, certainly complicated. Doom. I like doom. Lazy. Okay, I assume lazy means that we need to be mitigating climate change. That's the solution to climate change, not this. Okay, so it's hypocritical. Okay. So looks like risky, uncertainty, complicated, perhaps expensive to do. Okay, so let me take you through this topic just a little bit. So I'm not going to spend very much time. So do I have like 50 minutes or do I need to be done in it? Because I can adjust on the fly. Noonish. Okay. So I'm not going to spend very much time on this. This is perhaps one of the most important environmental data sets of the 20th and 21st centuries. This is the record of carbon dioxide concentration from the Mauna Loa Observatory in Hawaii. I'm sure you've all seen this. I think for 2025, the annual average concentration first in the week by volume or something 427, contrasted with about 313 when this record began in 1950. So this very steady, perhaps even accelerating over some periods of time, rise in greenhouse gas emissions, largely due to fossil fuel combustion. And that extra energy in the system trapped by these anthropogenic greenhouse gases does multiple things. Can melt ice, can evaporate moisture from the soil, but it also raises temperature. And we see that signal. See if I can do this. Is this the pointer? We see that signal very clearly in this temperature record. It goes back to the 1850s. Some more uncertainty in temperature records back that far, but quite a bit of confidence in this overall temperature record. And this is ending in the year 2025. The 11 warmest years on record have all occurred in the last 11 years. The warmest year on record is, 2024, followed by 2023, 2025. So we see a steady increase in global temperatures. So the Earth has a fever. This extra energy in the system is causing changes. It's putting stresses on both natural and human systems. And this is very, very well documented by, for instance, the IPCC assessments, or in the past, the US climate change assessments, right? And I'm not going to take the time to read all of this, but we can see, and we understand very well physically, how many of these impacts are rising because of this extra energy in your system. And as IPCC has gone along and observational records have become longer, we're now seeing this in literally every region of the globe. And every additional bit of warming matters. Again, for the sake of time, I'm not going to go into detail on this slide. This is from a special IPCC report in 2018, looking at risks for natural, managed, and human systems. You can read a sample of these systems along the x-axis, where the red and purple colors indicate more damage, more danger, more stress on the systems. So we're somewhere around 1.2, maybe 1.3, depending on the time period and the linear trend of warming to this point. And what the international climate community has been warning for quite some time is we need to take all the efforts that we can to try to limit future additional warming. The thought that these dangers, these stresses on systems are going to become much more pronounced when we reach about 1.5 degrees of warming, which is about a decade away, right? And by all means, do nearly everything that we can to limit that warming to 2 degrees or so. So how can we do this? Well, the first thing is to reduce atmospheric greenhouse gas concentrations. So I want to be very, very clear. Solar geoengineering, solar climate intervention is not a solution to the climate change problem. Okay, the solution to the climate change problem is reducing greenhouse gas concentrations in the atmosphere. The first step is at a global scale, significantly reducing greenhouse gas emissions. Other aspects come into play that we won't talk about today in much detail, such as carbon dioxide removal approaches, accelerating natural sinks of CO2, or using technology to do that. But this is what we have to do. The CO2 has a very, very long lifetime in the atmosphere. So even if we stop emitting greenhouse gases today, concentrations are going to stay very high. There's a commitment to climate change, if you will, through thermal inertia of the ocean. So things aren't going to get better instantly, but this is the solution to climate change. In contrast, something that we could do on a much quicker time scale is to increase the albedo of the planet. Okay, making the planet brighter to reflect some of the incoming solar radiation back out to space. And we could go into details on the Earth's energy budget. I'm not going to do that today, but this is the idea behind solar pocket intervention. So should we consider doing something like this while we get our act together and get serious about climate mitigation? And there is progress in mitigation. These are some of my favorite reports to read for the students in the audience or the professors if you haven't looked at it. This is from the United Nations Environment Program. Boy, I'm getting old, hard to see these start things. United Nations Environment Program called the GAP reports. And that's an appropriate name because it talks about the reductions that we need to make, the rate at which we need to be reducing greenhouse gas emissions in order to meet specific climate targets like 1.5 degrees or 2 degrees of warming. It's all based on the carbon budget. Very nice reports. And you can see from the titles, the closing window, the heat is on, broken record, that is becoming quite serious. So the reality is that, the world and many parts of the world are making progress and there's growth in things like renewables, but the progress is slow. Right? And it appears unavoidable that we're going to overshoot 1.5 degrees and perhaps 2 degrees if we don't get much more aggressive about this. So given that fact, there is an argument to be made. And I wish I could remember some of the words in the word cloud, but risky, crazy, scary. I don't disagree with that. But there's an argument to be made that given these growing risks, we need to understand the feasibility, efficacy, risks, and benefits of potential climate intervention strategies. Not arguing for deployment at this time, but we need to understand these things. My personal reason for studying this is having been involved in things like IPCC, being involved in UNEP, having the privilege of speaking with the UN General Secretary. These bodies, these groups want to know answers to these questions. So I think we need to do the research to be able to allow policymakers to make informed decisions. So climate intervention, sometimes called geoengineering. This is an accepted definition. This is a 2009 report on the topic. It's hard to read. Geoengineering the climate from the Royal Society in the UK. It's a really great report. It's still relevant today. You want to take a look at that. And they define it as the deliberate. This is something we would intentionally do. Large scale, we're talking about global climate, manipulation of the planetary environment to counteract, I think we should say, the impacts of climate change. Now, I refer to it as climate intervention because of these US National Academy reports, a dual set of reports that came out in 2015, one on carbon dioxide removal, the other on sunlight reflection, if you will. And they prefer the term climate intervention in place of geoengineering because it felt like engineering conveys a sense of control that is not there. The climate system is a very, very complicated system, right? If you perturb it in some way, it takes a lot of research, a lot of understanding, models, observations, anyway, to really understand what the potential implications might be. So it's a very challenging, but very important research topic. Intervention is an action that is meant to improve. I'm sure you guys have tried to intervene with Harvard, right? Sorry, Peter. It's just I've got it. Okay, so I'll go through this pretty quickly. So these are these 2015 reports. Carbon dioxide removal, one of the points I want to make is that is also a climate intervention. That is also geoengineering. We are intentionally intervening in the natural system to augment natural sinks and carbon dioxide removal. Perhaps we use technological solutions. You might have heard about these big scrubbing systems that, have been studied where you take in ambient air and use chemical processes to remove the carbon, we emit carbon-free air. These are interventions. And if we really scale this up at a magnitude that we need to make a meaningful impact on the carbon budgets, we don't really know what any of those environmental impacts might be. So carbon dioxide removal is a fascinating topic. In 2009, the academies came out with this really, really nice consensus study report. Negative emission technologies and reliable sequestration, carbon sequestration is part of this topic. And then for the oceanographers in the room, ocean-based carbon dioxide removal, Scott Stony shared this report in 2021. Really nice set of reports. This report on reflecting sunlight, this is the Academy study that I had the honor of participating in. I'd done no research on the topic at the time that I was on this committee, that I became interested in this topic, and that's how I got part of my group looking at this. So making recommendations, our charge was to develop a transdisciplinary, because there are social science, political science, many different aspects, governance considerations, legal implications. So much more than just physical climate understanding to this particular topic. It's the only academy study. I think I've been part of 6 or 7 academy studies over my career. It is by far the one that I had the least, I couldn't anticipate what the outcome was going to be. We had 18 people on this committee from all these different backgrounds. The word cloud that we did at the beginning, that was sort of the views, right? There were people coming in and saying, this is crazy, we should dissuade, we should not be thinking that the US should create a research program on this topic. And it was what an academy study should be. We spent about 2 years learning, debating, et cetera, before we made our recommendations. And at the end of the day, we were able to make consensus recommendations that I'll come back to at the end of the talk. So you can read some of the other works here, copies of the time. So this is just a cartoon that I really like from a paper that was published in PNAS a few years ago, I guess about 5 or 6 years ago, right now, that emphasizes the points that I've already made, right? This is the solution to climate change. We have to bend this curve downward. We have to reduce emissions. Oh, here. We have to reduce emissions of carbon dioxide. That is something we have to do. All of the IPCC scenarios that are, the various SSP scenarios are assuming large-scale carbon dioxide if we're going to try to limit this global warming to something like 2 degrees below. And we're not there yet. They're actually assuming very aggressive carbon dioxide scenarios. So most people believe that carbon dioxide removal has to be part of the future. There's a lot of interesting questions on that, if that's a topic you'd be interested in looking at. And so the idea is that if we do this, and if we start implementing CO2 removal approaches at scale, should we consider something like stratospheric aerosol injection, solar geoengineering, for some limited period of time to keep global temperatures at some, quote, safe level, 1.5 degrees, 2 degrees. A lot of discussions about what that would be. A lot of discussions about who would set the global thermostat. That's a lot of the equity and governance considerations. But should we do this for some period of time to minimize some of the harms, some of the damages from climate change? So that's the question. This is not a new topic. The academies in 2015 did not come up with this, or the Royal Society in 2009. Again, because of time, I'm not going to go through the history. I know a lot of people here know Wally Broker, who wrote a paper on this topic in the 1980s, talking about flying a suite of jumbo jets and using things like sulfur dioxide into the lower stratosphere to reflect sunlight. A colleague of mine from NCAR, Tom Wigley in the 2000s, and then Paul Crutzen I know people are probably quite familiar, certainly with Ken Starr, in the room, the atmospheric chemist, Nobel Peace Prize winning atmospheric chemist. In 2008, wrote something he called the escape route essay. And it dealt with this problem. He was not convinced that we were going to mitigate climate change at the magnitude of speed that we need to, and argued that we should be considering radical contingency plans, such as solar geoengineering. And Jim Hansen, you guys know Jim Hansen, like 1988 testified before Congress, alerted Congress to the dangers of anthropogenic climate change, and a very, very strong advocate for, warning about the dangers of climate change and an advocate for mitigation. And relatively recently, in Science Magazine talked about the fact that we may also need to do something along these lines. So, in terms of the Academy study, there are other approaches, putting mirrors in outer space, other kinds of things. The Royal Society report goes through all of the proposed technologies as well. But we focused primarily on 3: stratospheric aerosol injection, putting aerosols above the troposphere into the lower stratosphere to reflect sunlight. Marine cloud brightening, so especially over the stratocumulus cloud decks that occupy very large regions off the west coast of the continents that are semi-permanent. Proposals out there to try to brighten those clouds by injecting salt particles serving as aerosols. And then cirrus cloud thinning, which doesn't really reflect sunlight, but would allow more long-wave radiation to escape to space. Okay, by far and away, most of the literature has dealt with the first 2. With Steve in the room, I'm not going to try to say that I understand aerosols very well, but we do know that aerosols can directly scatter sunlight, and in that way they can help cool the planet, or there's the indirect cooling effects of aerosols, perhaps by brightening clouds, leaking more water droplets, minor water droplets that increase the albedo of clouds. So this is one example of the idea behind marine cloud brightening. Do any of the students in the room want to guess what produces these cloud streaks? This is off the west coast of the US. What are we looking at here? Come on, don't be shy.
I know, but I'm cheating, so it's someone else.
Yeah, you're cheating. Someone else. I agree. Yes. Ship tracks. Pardon me. Ship tracks, exactly. So we're looking at ship tracks here, right? So the analog is ship tracks, as these cargo ships are traversing the Pacific Ocean in this case. Emissions from these ships can serve as clouds, condensation nuclei, and can form cloud streaks, much like you see contrails from airplane traffic. So the idea here, what's being discussed in the literature, is can we take advantage of these massive cloud decks, these stratocumulus cloud decks, not put chemicals, but spray salt water into these clouds and brighten the clouds? For the aerosol experts in the audience, you know this, cloud aerosol interactions are a challenging topic. Our understanding is improving, but still there's many aspects that are not well understood. And we, generally speaking, very poorly represent these processes of climate models. So when you use climate models to conduct these experiments, to answer these what-if questions, right? That's one of the main challenges, in my opinion, of the marine cloud brightening studies. The other is stratospheric aerosol injection. This is perhaps the most studied approach, where the idea is to put some sort of a material into the lower stratosphere. The analog for this is volcanic eruption. And if you look at things like Mount Pinatubo, and you look at the temperature trace, this line here is when Pinatubo erupted, and this is a global average temperature over the lower portion of the troposphere. You can see a very pronounced cooling trend. Cooling perturbation, right? Almost about a half a degree from one volcanic eruption. And it lasted for about a year, or maybe 18 months of cooling. So the idea is, could we do something that essentially mimicked a volcano and maybe periodically inject particles into the stratosphere to keep the cooling at some level. This is just a little movie loop. Again, I don't want to spend too much time on it. That shows the Pinatubo eruption. You can see the dispersion of the aerosols. The time stamp is right here. So we're just kind of going through the month by day. And you can see from even a point location, because of the circulation in the stratosphere, how quickly you achieve near global coverage. Most of the aerosols are in the northern hemisphere because that's where Pinatubo was located. But the idea is you don't need to necessarily disperse aerosols all over the place. Maybe just a few point locations in the northern and perhaps in the southern hemisphere to achieve this. Okay. So I want to take you through a few results from my group quickly in the next 15 minutes or so, and then I'll wrap it up. So there's a whole bunch of experiments. There's a project called GeoMIP, a geoengineering model intercomparison project with various kinds of modeling scenarios and multiple groups. In my work, I'm going to primarily focus on the NCAR models, surprise, and two experiments that we have done. The first is called GLENS, and that's what I just showed you a movie of. I'm talking to you, by the way, this whole time.
It's okay.
I probably am. So GLENS, where stratospheric aerosol was started in the year 2020 to keep global temperatures at 2020 values, and then ARISE, which we started stratospheric aerosol injection in 2035, so out into the future, and to keep global temperatures essentially at that level of say 2030 to 2050. ARISE was contrasted with SSP 245, which is currently viewed as a fairly plausible, realistic future emission scenario. GLENS was contrasted with a scenario in which there's very little mitigation, RCP 8.5. So this is really hitting the system hard with a hammer, if you will, and ARISE maybe is something that's more plausible, like something maybe we could do by the year 2035. Yeah. I'm not going to read through all of this, but I just want to say, you know, I've talked about, we've done one particular experiment with one particular climate model or an ensemble of simulations of these. But the results are definitely scenario dependent, right? You have one set of results that we have a very aggressive geoengineering strategy to counteract a very high level of greenhouse gas warming with something like RCP 8.5. And the results are model dependent. Done some work with different models from GeoMIP, and these are real big issues. We'll try to draw conclusions about what stratospheric aerosol injection might do. So this is a kind of a summary that I put together of the three main goals of some of the work that we're doing at CSU. I want to start with a very quick review of this one. And that is, if someone were to deploy stratospheric aerosols, and we focus primarily on stratospheric aerosols, not marine cloud, right? Would we be able to detect that? And I don't mean detect the fact that aerosols or aerosol concentrations are increasing, but rather, would we be able to detect the impacts of it? Would we be able to detect, given the noise in the system on both weather timescales and climate timescales, would we be able to detect the impacts? And a good example of that is if I go to the GLENS scenario, which again, started aerosol injection in the year 2020, and we run a 20-member ensemble, right? And we average all those ensemble members together. This is the change in surface temperatures over North America the first decade after the deployment. It works, right? It works. There's no change in temperature. That's what we were trying to achieve. However, when you look at the individual simulations, this is the change in temperature after the first decade. So why do we have those big warming and cooling regions? Anybody? Parker, you can answer that one.
Variability.
Variability, right? Internal climate variability. Natural variations. And so PDO, the typical type of gale variability and the like. Right. So this in this context, we don't live in an ensemble average world. We live in one of these simulations. Okay. Would be able to tell whether or not stratospheric aerosol injection had been deployed. So I did this work with Lantau's son, who's a research scientist in my group, and Libby Barbs, who was a professor at CSU at the time. She moved to Boston University about a year ago, as head of a data science group at Boston. But we were looking at changes in extreme, so not mean temperature, but extreme temperature, extreme rainfall. And we asked a question using machine learning: how quickly or at all could a computer, by just sampling an individual run, be able to tell us if it was sampling a world with or without stratospheric aerosol injection? So again, when you look at the ensemble mean, this is Glenn's, and this is looking at the year 2030. You see that the blue colors here is probably a little bit hard to see. Don't worry about the details. The blue colors indicate that there is a decrease in temperature extremes, and that's what you would expect. Okay, the stratospheric aerosol injection. But if you look at any individual ensemble member, just to drive this point home, this is the year 2030 in one member under RCP 8.5, and this is the year 2030 with stratospheric aerosol injection, and this is the difference. Right? So some regions of the world have warmth relative to 2020, others have cooled in terms of temperature extremes, more frequent or fewer temperature extremes. Could a computer adequately look at those individual maps and say, I'm looking at a world with or without a SAI? It was an interesting exercise to do. And this is the result. And basically the darker colors indicate here for like the Glenn's SAI runs for extreme temperature. SAI runs in blue, RCP 8.5 runs in red. Very quickly, after about 5 years, okay, the machine learning model was able to very, very accurately say, I'm sampling a world with or without SAI. And when you look at extreme precipitation, it takes a little bit longer. There's a little more uncertainty, but within about a decade or so, the model was able to almost always predict the right world. And that's because there are regional signals, regional changes that the machine learning algorithm picks up on. This is one of my favorite papers. This is Antonio Mamalakis. He was a postdoc in working with me and Libby. He's now a professor at University of Virginia. And he asked 2 questions. Does SAI make the future climate look less different from today? In other words, how well does it actually preserve today's climate? I talk about in terms of global temperature, keeping it at 2020 values or 2035 values. And does it reduce climate change, or does it create a different kind of climate change? So this diagram takes a while to go through, and I'm happy to describe it to anyone after the talk in more detail. But again, we're using machine learning, and 50% accuracy here would be that the computer can't tell. Machine learning algorithms just flipping a coin. And higher levels of accuracy mean that it's very accurate, saying I'm sampling this world or that world. And you can see under climate change, which are the red dots, every variable, there's 21 variables that we looked at here, really changes, right? Future climate is very different under climate change. And under the blue dots, generally speaking, the blue dots are the SII world. And it's more, they're all below the red dots. So it's more like today's climate, but the computer can still tell that it's not today's climate. There are some variables that it struggles with a bit more, but by and large, the results of this study, I think, drive home a really important point. SAI can lead to a less distinguishable climate from pre-deployment than what will happen under climate change, but it still leads to a different type of climate. This is an example, again, so I like natural variability, right? And I try to understand natural climate variability. And this is a really straightforward concept. Pat Keyes, Noah Diffenbaugh, Libby, and Curtis Bell at the Naval War College, and I put this paper together. And it was just pointing out Now, these are using the ARISE simulation, so SAI deployment starts in 2035. That because of internal climate variability, if you look at any individual member of the ensemble, right? If you were living in Beijing climate, China, in this world, temperatures really wouldn't have been increasing since 2025, maybe even decreasing, but then you start to get warming thereafter. And this is because of internal climate variability. Or maybe you've been experiencing warming and that warming continues. So this is what we call perceived failure, right? And you can actually just compute the percent of the ensemble members where you have warming, rebound, or continued warming the decade after deployment. And the red areas are pushing about 50%, 50-50 chance. So the societal, the social science aspects of this, or the political aspects, are really interesting to consider. If the world were to do this, right, and policymakers living in these regions said, wait a minute, we're doing all of this, I thought the planet was going to cool with big warming, right? What are the implications of that? Okay, I'm not going to have time in 9 minutes to go through all this. I'm going to go through it very quickly. Again, happy to talk to you on after this presentation. Goal number 2, quantify changes to Earth system deployment. So we have looked at fire weather. This is Danielle Tuma, who was a postdoc with me. She's now a professor at University of Texas in Austin. She's an expert on fire weather conditions, and we're looking at how fire weather conditions might change in the future under SAI. The blue regions show that fire weather conditions favorable for fire decrease, the red where they increase. You see some mixed signals, and you see some time series of this. And these mixed signals arise from a variety of factors, changes in temperature, humidity, winds, rainfall, and this paper diagnoses that. The bottom line is, even with stratospheric aerosol injection, some regions may warm, fire weather conditions may get worse in some regions. This is Ariel Morrison, another postdoc in my group. She looked at Arctic permafrost, right? And essentially what she found was, while temperature stabilized, this is the temperature of the permafrost in the Arctic, stabilized relatively quickly, you continue to lose permafrost, even with stratospheric aerosol injection under this scenario. Because the warmest and most degraded permafrost is too deep underground to be strongly affected by changes in surface climate on these time scales. She also looked at Arctic shipping. And the idea is that if SCI preserves or restores the ice, what happens to future Arctic accessibility? This was a really interesting study because she did a lot of detailed work on what shipping companies actually take into consideration before they attempt to cross the Arctic. Most typically following the Northern Sea route here off the Russian coast, occasionally through the Northwest Passage, and very seldomly with the Central Arctic. But with climate change, the Central Arctic opening up would provide much opportunities for quicker shipping. So as you might expect, under climate change, these colors indicate that the sea ice thickness is decreasing, the oranges and the reds. The green colors indicate the number of navigable days across the Arctic. So much less sea ice, much thinner sea ice, more days that are open for shipping companies to go across the Arctic. If you look at SAI, those changes are much reduced. And if you look at a more aggressive aerosol injection strategy, where we would actually cool the planet down intentionally, the sea ice actually thickens in much fewer days than the Arctic is reversible. This is another study that I really enjoyed. This is with Daniel Hurrell, who was a PhD student of mine. He's now a professor at Colorado College. And in short, when you look at long control simulations, like last millennium simulations with the climate model, you can calculate what are called climate speeds. This is the rate at which ecosystems, both marine and terrestrial ecosystems, would need to move in order to stay in the same climate conditions. That makes sense, right? And a generally accepted value is speeds greater than 10 kilometers per year are too much for ecosystems to be able to achieve. So it's a great threat to ecosystems. And if you look at the pre-industrial control simulations, this is the percent of the globe that is exposed to climate speeds greater than 10 kilometers per year. In the ARISE simulations and the SAI simulations at 1.5, so setting to 2035 conditions, is well within this range of maximum exposure just due to natural climate variability. But when you look at climate change scenarios, you see climate speeds due to warming that are much greater than what ecosystems have been exposed to in the natural world. And also, if you look at a range of more aggressive stratospheric aerosol injections, you see that ecosystems would have to adjust to speeds much greater than they've witnessed in the past as well. So the bottom line is, you have to be very, very thoughtful about these things. You can't just cool the planet down to a degree, or maybe, why not go back to pre-industrial conditions? Because that cooling, that rapid cooling, would also present a very grave threat to ecosystems, just in the same way that rapid warming does. Oh boy, I really don't have time to go through this. I'm just going to say that we've done simulations of this with the WRF model as well. We've done what's known as pseudo global warming simulations, and we are the first group to do this, what we call pseudo SAI simulations, where basically you take some of the forcings from CSM, implement those in a weather model with a much finer spatial scale. I skip this, and it allows us to look at things like this. This is Wally Summers, who did a master's degree on this topic in my group, and we can actually look at things like severe weather outbreaks or strong mesoscale convective systems and ask how they might change. And this is just showing during this event, the super tornado outbreak of 2011. This is the observations of total daily precipitation. This is a simulation by the WRF model. I think you agree it's capturing the storm system quite well. So then you can look at things like how stratospheric aerosol injection and climate change both would affect the characteristics of events like this. Yeah, happy to go into the results in more detail. The final slide, pretty much the final slide, is we've also been thinking about scenario creation. And in particular, one of the topics that a lot of people are really interested in and concerned about is the possibility of unilateral flood. Some nation, group of nations, or maybe a billionaire like Paul Shepson would decide to try to save the world one day, right? There's very, few limitations on actually doing something like this through international and national laws. And so we've been studying some unilateral deployment scenarios. And we've written a paper on this. We've actually done a simulation. And the idea is to use game theory to assess which nations might have an interest in doing this, which nations might have the capability of doing this, which nations may be able to tolerate international pushback for doing this. It's a whole geopolitical science side of this problem. And then we've come up with some plausible scenarios, implemented those in the model, look at how the climate evolves, and then based on that, how would entities respond to that? Okay, would other groups do it? Et cetera, et cetera. So fascinating area to work in. Many unanswered questions yet. So this is what I'm going to wrap up with. So it's 11:59, Parker. I got a minute. Okay. So this is the Academy study that I served on that I talked about before. And the major recommendation of this, after all this debate, 2 years of learning about this topic, there was a consensus, there was unanimous agreement among the committee members. It was chaired by Chris Field, by the way, from Stanford, that the U.S. should establish, in coordination with other countries, right? We can't advise other countries with statements like this, a transdisciplinary research program that should focus on developing policy relevant knowledge rather than advancing a path for the thing. This was the U.S. National Academy of Sciences. The American Meteorological Society, if you're not aware, and AGU and other professional societies have statements on climate intervention research. This is AMS's statement. that says, you know, it recommends an accelerated and robust climate intervention research program to inform public policies. So very consistent with what the Academy's concluded. I had the opportunity to serve on a United Nations Environment Program analysis of this as well. I prepared a report for the UN General Secretary a few years ago. Andrea Hinwood is the chief scientist of UNEP, although I think she retired this month, or maybe last month. We wrote this report. I don't know about this word expert, but independent review on solar radiation modification, another term, solar radiation modification. And this is a really nice report that presents, in my view, a very balanced analysis of what we know, what we don't know, what we need to do to improve our knowledge. And then I was involved with WCRP for many years, and I was on the Joint Scientific Committee. And before we stepped down, we had this whole debate within the World Climate Research Program. Is this a topic that WCRP should actually engage in? Because it's been somewhat of a taboo topic, right? Does WCRP want to put its reputation out there and come down on saying that research is important? And at the end of the day, after a lot of debate, we decided to create a new activity on climate intervention, which is now part of WCRP. And as I said, IPCC is going to focus on climate intervention in its next assessment. This is a quote that I like. I'll just let you read it from a colleague of mine on the National Academy report. That can we be sure, absolutely sure, that we don't need this in the future? What if the impacts from climate warming just become too difficult to deal with? And if it turns out this is not a good idea, and I'm personally motivated by this as well, you know, I don't want to do this. I don't advocate for doing it right now. But if someone does do it, maybe, or considers it, I think the best way to dissuade that is by using the sound science that shows why it is bad. I'm not just saying it's a crazy idea. So, one more question. Does it give you some sense of hope and opportunity? Maybe we avoid some of the worst impacts. Maybe we can buy time for mitigation efforts. It's worth the so-called risk. You support doing research on this topic, or are you not sold on this? And that is a perfectly fine answer, right? You're afraid of what's called the moral hazard, that it may reduce the commitment to mitigation. I can address that question if you want. The potential risk outweigh benefits. How on earth are you going to govern something like this? Right, that is a huge challenge. So maybe we shouldn't even do research, or just do very good research. So, oh, that's not the right one. Okay, so I'm curious whether you sense hope and opportunity or fear and distraction. So thank you. I think there might be a Q&A slide. I don't know if you look at your phone. If there is, you can type questions into that. And I can either get to the questions later, but it's kind of fun because you can upload or download. You know, Paul asked the question, load it down. Silly question. Right. So thank you. And I just want to repeat what I said at the beginning. I am so honored and pleased to be here. It truly, genuinely means a lot to me to be invited by the speaker. So thank you all so much for having me. Oh. Happy to take any questions.
So hopefully we can have the student question as well. Okay.
Hi, yeah, that was great talk. You kind of touched on the idea of I was wondering, that's what I say is the best approach. Whether, for example, for the trade, there are some questions in place, not really have certain states may try to put whether or
Can I just say that is such a interesting but complicated aspect of this whole thing, right? the question is, about the governance. Even in the US, we live this way, some states have banned activities on this. There's a lot of concern about even testing some of these ideas. Even, in the Academy's report, we made recommendations that if you can't learn it from a model, if you can't learn it in the laboratory, maybe some small scale field deployments are going to be necessary to fill in some of the scientific gaps. But we were very careful to put parameters around those proposals so that there would be no effect on weather, no effect on climate, right? So, that's kind of how I feel about some of those field experiments. It's a very good question, and I'm not going to pretend to know the answers to how you navigate the complex geopolitical governance issues around this. All I do know, one of the things that motivates me is that there are people, there are governments that consider things. There's even some startup companies you might have heard about, one called Stardust, Israeli company, where they're developing the technologies to do something like this, to sell them to interested parties who I think about this. There's another called Making Sunsets, if you've heard about that, kind of a one-off effort than trying to sell cooling credits. So this stuff is happening, and I really look to my colleagues in political science to solve the governance issues. That's a huge challenge, and in fact, I think one of the most compelling arguments that this won't ever happen, because it's hard for me to imagine the world coming to agreement between us and each other. I recognize that, but I just also know that I'm being asked questions by U.S. government, by other governments. What do we make of this? So I think we have to be able to answer those questions. Yes.
How much does this cost?
It all
how do you
depends.
do,
It all depends on how you were to do it. Right?
yes.
But one of the ideas behind stratospheric aerosol injection is you would need one way to do it would be a fleet of planes that would deliver the aerosols to the stratosphere periodically. And I can't remember the exact numbers, but most of the people who study this is relative to the cost of other things like wars, right? It's not very much money.
The planes are going to have their own effect.
Well, yeah, and that's none of this
It's all
is a perfect
relative.
solution, right? Now, if you are instead going to advocate for putting gears in outer space, right? That's going to cost a lot more, right? And the estimates for that, the Royal Society report that I alluded to provides some cost estimates. Since now it's 17 years old, so take those estimates with a bit of a grain of salt. But yeah,
I can just say I mean, of course, there's a lot of uncertainty, but it's on the order of maybe $10 billion a year or something. It's basically nothing, like a billionaire could do it, that's smart.
It's a ballroom.
Yeah.
these conversations always go this way. Paul had his hand up
Okay.
first, and
Well, first, thanks so much for being here. It feels almost surreal yet wonderful having you here at Stony. So it was a great talk. So let's imagine that we do SAI for, a couple decades, something like that, and we realize there are unintended side effects of this drug, and we want to wean ourselves, and we need to do it relatively quickly. To what extent have we used models to address the question about environmental impacts of withdrawal?
so we have used models to run those experiments. My research group hasn't done those experiments, but other groups have. I think what you're broadly referring to is often called the termination effect. So if greenhouse gases are continuing to increase in the atmosphere, that leads to more energy in the system. And we're kind of like putting a Band-Aid on that problem by doing stratospheric aerosol injection, and then we go, whoa, that was a bad idea, let's stop doing that. The climate system is going to rapidly warm up. We're going to have very dramatic changes on a relatively short time scale. That will present all kinds of significant risks to things like ecosystems. So this is a big concern, which going back to that cartoon that I showed. You know, the arguments for this, when this would even be considered, are fairly complex, but one of the arguments, that's why I use the words, you may not have picked up on it, that you shouldn't even consider this until we are bending that emission curve downward, right? And only at that point, maybe we consider doing this. But as long as the world's not making that, I would argue, no matter how beneficial it might look, I would argue against doing it. Because if you do stop doing it at that point, you're setting yourself up for some trouble. You want,
Yes, hi Jim, thank you for the talk. So in your Arisi and Glenn scenario, I guess you needed to increase the injection year by year in order to maintain the temperature.
Yeah.
I'm wondering whether you have any estimate like how many peanut tuber type of aerosols
Yeah.
will be needed.
well, so again, the answer to that question is at what point in the future are you? And it's all dependent on the emission scenario. So yeah, but in those experiments against RCP 8.5, and those simulations were run out and it was the equivalent of about 1 pinnitubo, but every year, 1 pinnitubo per year.
So technically, it's actually doable.
What'd you say, Paul?
Right, I did, I'm just recognizing it was,
Okay.
it's still what that feels.
Yeah. Yes.
You did, that was fantastic. I have a question, and I loved all the comparisons with the wildfire frequencies, you know, running the model out. Have you done anything closely looking though at the vegetation index? Just because obviously just showing those numbers with the amount of migration necessary in some cases for, I don't know, I guess that was on issues of biomes.
That was broad, sort of broad ecological parameters.
It's
Not,
yeah, but just given the range of variability, it seems like there could be ecological collapse. You know, but I don't know though, because just, you know, thinking about how
like
biomes.
right.
Right, most definitely, but I was just wondering if you, I was thinking of Lovelock. And I was thinking of, you know, just the biosphere atmosphere, you know, relationship and how to integrate that a little bit more.
So, other work that my group has done has been looking at agricultural impacts for, you know, crops like maize, rice, and sustainable crops like that. Ariel Morrison has also written a paper looking at the impact on luxury crops like grape production, coffee production. I told her she's going to have the most highly cited paper ever because everyone wants to know what's going to happen to their chocolate and coffee and things like that. But outside of that work, to be honest, we haven't looked at that too much. I will say that all of these simulations that have been run, as is often the case, this much of the data has been looked at, right? They are fully integrated Earth system models. We have crops in these models, we have dynamic vegetation, trees grow and die, plants move, and all that kind of stuff. There's a ton of stuff to look at, and we have not looked at all of it by any stretch. We still do look for something. So you can only do so much in a given year.
That looks like an
But
exciting field.
if you would like to, happy to, the data sets are freely available. Like NCAR always does, right? For runs and simulations, it's freely available for the community to access. So if you're interested, think about it. Yes.
I have a follow-up comments. Is there any like roughly estimations of how the this climate implications act on the CO2 concentrations? Considering the ecosystem
Yeah, no, that's a really great, like how the carbon budget and stuff like that would be impacted. So these runs have sort of the prescribed, you know, like RCP or SSP scenarios to prescribe that. But there are other roads that, first by the name Peter Moritz at ACAR, has been doing some simulations, just putting conditions out there and letting the system evolve, looking at the impacts on things like that. But I don't know what those results look like. But people are thinking that's a really important question. People are thinking about that. Yes.
Have you looked at any simulations, or is it even possible to do them for you? And like, so I get the idea of what happens if you put these aerosols in, but what happens if we have compounding events? So like, these are out there, but then we have like another Mount Pinatubo or another caldera, something else that goes up. Like,
Great. That's a great question, right? So how do you deal with that? What if you enter into some period of enhanced volcanism, right? And you're adding a lot more aerosols. So in the model world, of course, we can determine when volcanoes go off. And off, right? In the model world, though, what these ones are done with is something called a controller, a controller. It's developed by Doug Martin, Colloquium, and Hurrell. And it's constantly tracking the evolution of the atmosphere, and you can set certain climate targets. They don't have to be just temperature related, but in these simulations, it's maintaining global mean temperature at some level, maintaining more south radial temperature gradients and things along those lines. And then it's constantly adjusting. And so they did some runs where they did say, okay, now let's fire off a Pinatubo or 2040. Yeah. And in the model world, that's easy, right? So now the controller goes, oh, wow, we have enough aerosols. Right? That. So, you know, in the real world, I'm thinking off the top of my head, you know, that would have to be something, if you set up an intelligent way of doing this, well-governed system, some sort of that kind of monitoring would have to go on. So you would say, you know, and you could do quick follow-ups or whatever, and say, okay, we need to adjust the injection frequency. So, but it's a really, really great question. I mean, there's all kinds of those kind of risks associated.
I think the pizza is gonna get cold. Thank you so much.